I'll begin. Heavenly Father, we thank you for this day. Thank you for these students. Just pray that you be with us today. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. So we're about to start into our study of systems of differential equations. And before I do that, I just need to take about an hour of our time or so and just talk to you about matrices. All right? So this part of the course more or less is like a super condensed, just the most important parts of Math 221 lecture. Okay, so, but I hope you like it, I don't know. So here in a nutshell is matrices. Now I say it's just the Math 221, but in the same sense it's not really. So what is a matrix? All right, so a matrix, let's say an m by n matrix of objects is something like this. A equals to, so you have A11, A12, A1n, A21, A22, A2n. So here we have AM1, AM2, AMN. Sometimes you express this more compactly like this, AIJ with the brackets. So in short, a matrix is some sort of box of objects. It's an array of objects. It keeps track of rows and columns. How many rows here are there? So we have m rows, n columns, right? So for example, the ith column of A is equal to, what is it equal to? The ith column of A, you have to imagine, like here's the first column, right? Here's the second column. That's the nth column. The ith column, you have the second index fixed, right? 1, 1, 1, 2, 2, 2, n, n, n. See that? So it's just A1I, A2I, dot, 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 AMI. There you go. That's the ith column of A. What's the jth row of A? Actually, let me do it down here. Sorry if this is boring to start with, but we have to settle these terms. Otherwise, what I do a little bit later will soon become meaningless to you, right? How about the jth row of A? Yeah, we do what? Like here's the first row. You notice that 1 is the same? Or the second row, 2, the first index is fixed here. So it's, would you say I1? And I put commas here sometimes if I want to. AI2. Commas are, depends on, some people drop the commas here. Depends on context. But anyway, IN, right? Now, let's see here. So this first one, this is for what? For 1 less than or equal to I less than or equal to blank. And this one is good for 1 less than or equal to J less than or equal to blank. In other words, if you look at I ranges from what? From 1 all the way up to n. We have n columns. And how many rows do we have? We've got m rows. Right. Now, just to introduce some sort of like general notation, so let me call the objects that we're looking at S. All right. So with that notation, this A is an element of S m by n. So it's a matrix. The ith column is an element of what then? It's an element of S. What kind of thing is this? It's got m rows, right? But it's got one column. So this is an S m by 1. And down here you have an element of S 1 by n, because we have one row and n columns. So rows and columns are special kind of matrices, all right? I'm being deliberately vague here with S. So in Math 221, or your typical linear algebra course, you'll usually let S equal the real numbers, all right? But in here, we'd like to allow S to be other things that are a little bit more out there. Like I might want to let S have complex numbers in it, for example. I might want to let S have functions in it. So let me give you some examples of matrices here for us. Let me say example 1. We could have A equal to something like t squared, t cubed, t to the 4th, right? This is a 2 by 2 matrix of functions, all right? You could have, let's see here, B equal to, I don't know, you could have 3, 4, 5, 6, 7, 8 like this, all right? This would be a what? This is a element of, well, really just R, what? 2 rows, 3 columns, so 2 by 3. But the reason I'm being a little bit vague here is I want to allow the matrix to either have functions in it or numbers in it, okay? Because we like to work with matrices of functions in here. So part of my goal today is to explain to you not just the algebra of matrices, in other words, how to add them, multiply them, things like that, but also how we can do calculus on matrices of functions. The answer is it's not that hard, actually. So let me remind you something. You guys know how to take the dot product of vectors, right? So if you have vector v dot vector w, how's it go? It's v1 w1 plus v2 w2 plus da 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 plus vn wn, right? But you can also write this as what's called excuse me, words. You can write this as this row vector v1 dot 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 vn times this column vector w1 w2 dot 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 wn. So this is essentially a definition, is that v dot w defines the product of the row vector v1 through vn and the column vector w1 through wn. So here's the math here. We're looking at 1 by n matrix times an n by 1 matrix, and we get a 1 by 1 matrix, okay? So the product of a row vector and a column vector is just a number again. And of course, you know this is the dot product, right? Okay. So we can use the dot product basically to define how to multiply matrices. I guess I should stop and take a second. Do you know how to add matrices and multiply matrices by a number? I guess I should talk about that briefly. How would you add matrices? Yes, the way you would expect. You add them component-wise. If you take a matrix times a number, what's that do? Like if I took up here, I can squeeze this in without cramping my style much. What if I did like 3a? What would that be? The way it works is you multiply 3 on every component. That's the definition. So in order to factor a number out of the matrix, more interestingly, you need it on every single entry, otherwise you can't factor it out. Here, to give a slightly more interesting example up here, I could multiply b by the exponential function of time. I could multiply e to the t times b, and then that would give me a matrix of functions. This you will not do in Math 221. I don't think, anyway. Maybe if I was teaching it. I don't know. Let's see here. Although I was just talking to Dr. Smith, he has picked an interesting book for next semester. Let's see here. Anyway, okay, so we can scalar multiply matrices. We can add them. All right. I won't even write that down. And then, of course, we can take dot products. But then we can use dot products to define the product of matrices, provided that they have like the right kind of matching sizes. So let's see here, multiplying matrices. Let's talk about that. When can you do it? When can't you do it? How does it work? So I'm just going to give you an example of how it works to start with. Then I'll give you a general definition, and then I'll prove some properties about it. So let's see. Suppose you've got 1, 2, 3, 4. All right. And I'm going to multiply that by, we'll start out simple. We'll start out with a column. So let's say 5, 6. All right. How do you multiply a column vector times a matrix? So what you do is you just do basically the vector 1, 2 dot product with the vector 5, 6, and then you do the vector 3, 4 dot product with the vector 5, 6. I don't usually write down in black what I just wrote. I'm just showing you that that's the mechanics of the matrix multiplication as it relates to dot products. So I visualize that like this. I take 5, 6, and then I multiply by 1, 2, right? And that gives me 1 times 5 plus 2 times 6, which is 12. Down here I get 3 times 5, which is 15, plus 4 times 6, which is 24. So what do we get? We get 17, and we get 39. All right. How about this? What if I take same matrix, 1, 2, 3, 4, and I multiply it by, let's say, 0, 1. I'm going to skip the in-between step and just get straight to it. What does that give us? So I get 0 times 1 plus 2 times 1, which is 2. And here I get 0 times, here I get 4, right? Because I get 0 times 3 plus 4 times 1, which is 4. Right? Oh, I guess while we're at it, what do we also have? 1, 2, 3, 4 times 1, 0. What's that give us? 1, and then 3, because sorry, my numbers are getting too scrunched. Well, if I have trouble separating the numbers, sometimes I'll put in a divider. That's just decorative. But I find that's helpful, especially when I have like functions that have several summands, to put in the divider. But anyway, answer is 1, 3 here. Okay, so all of these are what are called matrix column products. These are examples of matrix column products. In other words, we're looking at the product of a square matrix by a vector, a column vector of the same size. And what's the output? Is another column vector of the same size. So how does that, what's the counting here? Basically, we have 2 by 2 times a 2 by 1 vector, right? And the output is a 2 by 1 vector again. Let me show you another example before I get to the general definition. Example 4. If we look at 1, 2, 3, 4 times 5, 6, 0, 1, what do we get? So the way this works, and I'm going to write this out. All right, so this is, you have 1, 2 dotted with 5, 6. This one gives us 3, 4, dotted with 5, 6. 1, 2, dotted with 0, 1. And 3, 4, dotted with 0, 1. This is the definition, if you like, of matrix multiplication, okay? You take dot products of the appropriate rows and columns of the matrices being multiplied. So to find the 1, 1 spot, I take the first column of the right product, dot product with the top row of the left thing. I'll make this more precise in just a second here. But what does this work out to? Well, if you look at this, this is exactly what? Hey, we've seen this before, right? See, this is exactly that, right? So you already know what that works out to, 17, 39. And by the way, this second thing is just going to work out to 2, 4. So bigger picture stuff here, 2 by 2 matrix times a 2 by 2 matrix gives you a 2 by 2 matrix, right? So in order to multiply two matrices, we must have the size of the rows of the left factor matches the size of the columns of the right factor. So here's the definition. If A is m by n and B is n by p, let's say, then A times B is a m by p matrix where A, B, the ijth component, all right, is given by row I of A dot product with column J of B. That definition makes sense because the size of the row and the size of the column has to match up in order for the matrices to be what are called multipliable. This condition that we have, matching dimensions for A, m by n and n by p here, the fact that the n, which is what? What is n here? So n, as it relates to A, is what? That's the number of columns, right? But that also gives you the size of each row, right? The number of the columns is the length of each row. And the n, the second n here, is the number of rows in the right factor, right? But that's also the size of the columns here. So these are of matching dimension, which means we can take the dot product of them, right? If you try to do this in the wrong way on a TI calculator, what it will tell you? It will tell you, dimension mismatch, dimension mismatch. We've all seen it, right? I don't know. That comment is soon going to go by the wayside because how much longer are we going to be using these overpriced, antiquated calculators? I don't know. I guess as long as dumber than a box of rocks public schools dump money into them. But so I guess it's a question really for how effective the lobbying efforts are by Texas Instruments as they relate to the centralized education that we're about to enter into in this new brave America. Let's see here. I digress. Where was I? Okay, so now this definition is not near and dear to my heart. I mean, it's okay, but you could rewrite this, right? This is the sum over k equals 1 to n of row I of A, the kth component of that, times column J of B, the kth component of that. See, that's how a dot product works, right? 1 with 1, 2 with 2, 3 with 3, n with n, you add them up. Right? So a formula for that is just, I can rewrite this, the sum k equals 1 to n of VI WI, right? So I'm just using sorry, K, VK, WK. So I'm just using that over here, right? Do you guys follow me? But what this is, right, is just a stone cold formula for the matrix multiplication. I was about to put an infinity there. I've been doing too much series and convergence and divergence in Calc 2 right now. It's messing with my brain. So this is a finite sum. This is a harmless, innocuous, lovable fuzzball. Let's see here. So what's the kth component of rho I? The kth component of rho I is a sub ik, right? And what's the jth component, the kth component of column J? It's exactly B sub kj. You can see that by just looking back at the formulas I wrote over there, right? And this, honestly, folks, this is my go-to formula for the definition of the product of two matrices. This one is where, this one allows me to prove things about properties of matrix multiplication in the best way. Any questions before I go on here? A popular notation that I should probably mention here is sometimes when we want to talk about a matrix in terms of gluing things together, like this, we can go back and say that this is like A1, A2, AN. So this is, I'm viewing A as a so-called concatenation. Concatenation, just fancy word for gluing the columns together to make a big matrix, all right? So it's the concatenation of all the columns. It's just the gluing together of the columns. There's n columns, you glue them together. Of course, you could also look at this as what? I don't want to, let's just say row 1, row 2, row, how many? M. So you could also look at as the concatenation of the rows like that. All right. So in view of that, if I call this thing, I just want to point out a pattern to you before I end up inadvertently erasing something before I make the point. So if this is A, right, and if I call this vector v1, and if I call this vector v2, you'll forgive me if I don't put vector signs on vectors because it gets really old really fast here. So context, vector, vector. So what we've observed here, right, is the following property, is that A times the matrix formed by gluing together v1 and v2 is actually equal to AV1 concatenated with AV2. See, because this was A times 5, 6, and this was actually A times 0, 1 up there, right? Oh well. It was nice. You know, in a room with as few boards as this one does, and the material we're going over right now, I will have regrets. It's just an inevitability. Yeah, I guess we don't need this. So there I gave you the definition of matrix multiplication. Let me get around to giving you the definition of scalar multiplication and addition while we're at it. Probably pick up the pace. I do want to get to differential equations eventually here. So, definition, A plus B ij is equal to aij plus bij. If you take a scalar times A, it's equal to C times aij. And of course, this is for, well, I don't want to, let me just say this for matrices that In order for that to make sense, you have to have the same number of rows and columns to add them, all right? And, well, the scalar multiplication speaks for itself, I think. But all right, so here's some properties. So let's say for A and B, well, I really don't want to commit to that. Let's see here. So first of all, if I have A plus B, all right, times C, that turns out to be equal to AC plus BC. Now here A and B have to have the same size, right? And C has to be multipliable by that size. Likewise, if I have A times B plus C, well, that's AB plus AC, all right? These are not particularly surprising. 3, if I have A times, oh man, I don't know if I need all this. Well, I'm going to do it. A times EI, this is the ith column of A, where EI is equal to 0, and zeros all the way until there's a 1, and then zeros again. So this is the ith spot. Now, for that to make sense, it's not a row vector, okay? So how do you change a row vector into a column vector? Like, this is not yet true. So the way to change a row vector into a column vector, we have a notation for that. It's called the transpose. So you stick a sub t, like upper T here. What that means is that it takes the matrix and it switches it from m by n to n by m. So it switches rows to columns, is what it does. And so we've seen this 3 in action in the example over that we just worked, right? Like this right here, I want my pan over, Luke. This right here was A times E1 is equal to the column 1 of A, right? And this right here was actually A times E2 is, wait a minute, I can't do math. This is A times E1 is column 1, right? What's the other one? I'm a doofus. That's not E1, this is E2. It's a 0 in the first spot, a 1 in the second spot. So this is E2, and that gave us, of course, column 2. Right? So this is important. This is kind of like a, so if I want to select a column, I just multiply by the corresponding vector with just 1 in that ith spot. What happens? Well, okay, I've got about 13 things like this I can say. I'm going to behave and stop there. Okay, I'll misbehave a little bit. EI transpose times A, you know what that gives you? That gives you actually the ith row of A. But anyway, now I'm digressing. So 4 was the digression. Sorry about that. I should get it out of my system, but it's too late. So what happens, 5, another thing we know is that if we take A times, well, let's see here. So the concatenation proposition. So A times B. All right. In other words, A times B1, B2. Let's suppose Bn. All right. Suppose like that. Then there's a proposition, a pattern we've already exhibited for the example over there, which says that you can multiply it by just multiplying the columns separately. So this is A times B1, A times B2, A times Bn, like that. So this is what I refer to as the concatenation proposition. So the product of two multipliable matrices can be rewritten as the product of the left matrix by each separate column of the right matrix glued together in this way. It's really quite wonderful. So 6, I would just point out, if we look at A times E1, E2, En, how's that work? And this I'm actually going to prove, well, calculate. So by 5, what is this? If you believe me about 5, and if you don't believe me, I can prove it to you, but that would kind of be beside the point here. So A1, A2, right? And what are those? By 3, that's column 1 of A, column 2 of A, column N of A. So what is that? Right, that's just A again. So that's why we call this matrix here, right, is the so-called identity matrix. So the identity matrix I, or sometimes I sub n if you want context, is 1, 0, 0, 1, and then 1's down the diagonal. So, or sometimes when people want to write a matrix like this, they'll do something like this: 1's down the diagonal, and then like 0. This is a common notation. So, for example, I2, 1, 0, 0, 1, right? Or I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. So this identity matrix behaves like the number 1 for matrix multiplication. So like, pretty easy theorem to prove is that I times x is equal to x times I for any matrix x. Now, of course, x has to have the size which matches the identity matrix. They have to be multipliable, but excuse me, thinking of x as a square matrix here mostly. All right, so then this gives you a definition, getting to the point here. A is invertible if there is another matrix B such that A times B is equal to the identity matrix, and that's also equal to B times A. Okay. We have a notation. If this is the case, then we say B is equal to, we write B is equal to A inverse. All right. Yeah, Luke?
Can we have an identity matrix for non-square matrices?
Well, yeah, I mean, I can multiply the identity matrix times an appropriately sized matrix, like, 1, 0, 0, 1, as long as I've got, 2, 3, 4, 5, 6, 7. I could multiply that because it's still 2 by 2 times 2 by 3. But is there an inverse to a rectangular matrix? Yes, there is some notion of that, but not in the elementary discussion. I mean, I think that would be given to you by something called the Moore-Penrose inverse and something called the singular value decomposition. That's a little bit involved. I might get to that at the end of linear algebra next semester. I don't always get to it. Okay, so, but for square matrices, we're assuming that's a good, thank you for that question. By the way, you made me remember here, A is n by n matrix. It's a square matrix, okay? So that's a nice term, right? Square matrix is square. Makes sense, right? So the problem of finding an inverse for a matrix is a pain. Generally speaking, it requires a lot of calculation, but important case, there's a formula for the 2 by 2 matrix. So this is a gift, a beautiful formula for the 2 by 2 inverse. It's just this. And I think I may have showed you this, guys, before, right? I think this came up because we had to solve a 2 by 2 system in variation of parameters, right? So, in some sense, I should engineer the course so this comes before variation of parameters. Then you'd have some experience with matrix stuff before we do it there. But, you know, that's a kind of a small point in the big scheme of things here. So, anyway, there is actually a formula for the 2 by 2 inverse, just like that. So you see the 2 by 2 inverse exists only if what? So it exists if and only if AD minus BC, which, by the way, is the determinant of ABCD, is not equal to 0. If the determinant is 0, that means that the matrix is not invertible, or we say it's singular. All right. And that condition holds for n by n matrices as well. If you calculate the determinant of an n by n matrix, if it's non-zero, then their inverse exists. I don't want to describe how to calculate it in here for you guys, but you learn that in the linear algebra course, all right? It's involved. So what's the point? So now we have the toys, we can play with them. Let me just do one more. Let me do one more thing at this level, and then I'll talk about systems of equations and then systems of differential equations, hopefully. I've spent a little bit of time on the concatenation proposition here because that's something we use in differential equations a lot as we study systems. That actually is an important calculational step. I wanted to make sure you don't find it mystical. Okay, because when we do it in differential equations, we'll do it with a matrix of functions times a column vector of functions, so it gets to be a little bit more, I don't know, intimidating, I guess. But another definition, just to be clear, if we have an m by n matrix, then a transpose is an n by m matrix. So this is like m by n, this is n by n, as in nanu nanu and mummy. Let's see here. So a transpose, all right, ji is just equal to a ij, all right. That's for 1 less than or equal to I, less than or equal to m, and 1 less than or equal to j, less than or equal to n. In my current lingo there. So this is, the transpose of matrix is important. We've already seen the importance as it relates to just the, the formula for the dot product, right? Remember I showed you is the dot product of the, so to take the dot product of a column vector with another column vector, you take the transpose of the column vector and then multiply it by the column vector. So transpose comes up in the formula for the dot product, among other places. There's a really nice theorem. This is the so-called Sock-Shoes theorem. So AB transpose is B transpose A transpose is here's the proof. This will be the last of these sorts of proofs I do in here. But if we look at AB transpose and look at the, let's say, jith component of that, that would be equal to AB, the ijth component, right? By definition of transpose. But then this is the sum, k equals 1 to n, of a, I, k, b, k, j. Now if I do need to assume that a and b are multipliable, right? This is for what? For a, m by p, and b, p by n, okay? Oh, I'm sorry. M by n, n by p. So I'm making these match up. That's where the sum come from, right? Okay, and then this Well, oh man. Oh. Well, this is equal to the sum, k equals 1 to n, of b, kj, aik. What did I do there? You know, the point of these kinds of formulas is that these are just numbers. So inside this sum, I can switch their order and it's okay. One of the things I haven't shown you is that matrix multiplication doesn't work like this. It is not the case that AB times BA is necessarily equal. It happens to be here. These are special. But generally speaking, generically speaking, if I take A1 and A2 matrices, A1 times A2 is not equal to A2 times A1. The matrix multiplication does not commute, usually. So, but these are components. These are numbers or functions, and these do commute, always. Because numbers and functions, we can just... So I can do this step here. This is just properties of either numbers or functions, depends on what my matrix is made of. And then I use the definition of transpose again. So this is B, what is this, B transpose what? B transpose, JK. And then that's A transpose KI, right? But this, by the definition of matrix multiplication, is the sum k equals 1 to n. Oh, good grief. What am I doing? No. This is exactly B transpose times A transpose, right? The jith component. And so this is how the proofs work at this level of notation. I've shown that the jith component of that is equal to the jith component of this. So it follows that AB transpose is B transpose A transpose. Okay? This is so-called sock-shoes identity for transpose. By the way, the same sort of thing happens for inverses. AB inverse, if A and B have inverses, is B inverse A inverse. It's also the case. All right. So, I feel like I was getting better. No. Maybe I just can only lecture for about an hour before it starts to get me. Maybe that's it. I don't know. We're only at 45 minutes, though. So, actually less. I think I'm entitled to a couple extra minutes today due to our visitor. I mean, you're entitled to a couple extra minutes. What I'm talking about. Not me. It's your course. I already know this stuff. I think. All right, so what does this have to do with systems of equations anyway? Those are the main tools. These are the main tricks and formulas that are important to matrix algebra that we use to solve systems and analyze them, all right? Also, okay, fine, there's one other thing I should say. I'm negligent not to say this. This is kind of important, big deal. The determinant of a product is the product of the determinants. Like this is huge. You know, the determinant of the identity matrix is 1. That also is big. Those will come up in due time. All right. So now that we've gotten our feet wet and got some notion of what a matrix is, how to multiply them, what are their columns and rows and all that, let's talk about systems of equations. So, of course, algebraic system looks like what? It's like x1, it's a11, x1 plus a12, x2, plus a1n, xn equals to b1, and so forth. If I have m equations in n unknowns, looks like this. So here we have m equations in n unknowns. So basically, this is the system can be recast as what? It can be recast as a matrix, A11, A12, A1n, AM1, AM2, AMN, times this vector. So this system of scalar equations, right? These are linear equations. It could be recast as a single vector equation is the point. All right, single matrix equation. So this guy is what? This is called the coefficient matrix, right? This is the vector of unknowns. And over here, you have the inhomogeneous term. If all the b's happen to be 0, the system of equations is said to be homogeneous. Homogeneous equations are nice. They always have a solution. 0 is always a solution, right? So basically, what we learned in linear algebra is that to solve this, what's the method to solve this? To solve, you just calculate the reduced row echelon form of A with B concatenated on it, and this gives you the solution. Can be read off. Here, I'll give you an example. If I had x plus y plus z equal to 6, and if I had x plus 2y minus c equal to 2, and if I had x plus z equal to 4, right? If that was my system of equations, I can look at the reduced row echelon form of the so-called, this is the augmented coefficient matrix right here. Augmented coefficient matrix. So you calculate the reduced row echelon form of the augmented coefficient matrix. In this case, you do 1, 1, 1, 6, 1, 2, minus 1, 2, 1, 0, 1, 4. All right. And, that's your favorite Texas Instrument calculator will have that in there. There are any number of websites, blah, 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 blah. What will come out is 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3. How do I know that? Well, I made this system up with the solution x equals 1, y equals 2, z equals 3. And that's why I put a 6 here, because I know 1 plus 2 is 3, 3 plus 3 is 6. I know 1 plus 4 is 5, 5 minus 3 is 2, and I know that 1 plus 3 is 4. So I know that this will happen because what this says is that system of equations is equivalent to the system of equations x equals to 1, y equals to 2, and z equals to 3. This last system of equations I wrote is very nice because it can you see what the solution is, right? Excuse me. All right, so that's how to solve systems in a nutshell. So we're not interested in this per se. We're interested in systems of differential equations, right? In fact, I'm not going to test on this. I'm just telling you for your own informational purposes, this is how you solve linear systems, the fastest. Row reduction, Gaussian elimination is what this is. That's how you actually implement that by hand. So we are interested in a related but different problem. What we want to learn is how do you solve. So what we're going to have is something like A11 x1 plus A12 x2 A1 n xn equal to, let's say, f1, a21 x2 plus a22 x2, a2n xn equals to f2, and so forth and so on. But we're not going to look at this. I mean, in linear algebra is fine to look at 3 equations and 2 unknowns, or 4 equations and 6 unknowns, or whatever. Those are interesting questions for linear algebra. And here we're a little bit more focused. We're only going to look at n differential equations in n unknowns. Like, so the total order of the differential equation will match the total number. I mean, let me just write out. So in other words, my sort of number of rows and number of columns will match for what we look at, okay? So a n1 x1, a n2 x2 plus da 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 plus a n n xn is equal to fn. We're interested in how do we solve this. So what we're looking at below here is a so-called system of first order ODEs in so-called normal form. Actually, it's not quite yet normal form. I don't know. This is now we're quibbling. Is this? I would say some people would say this is scalar normal form, and I still haven't done it right. Curses. Man. What's missing from this differential equation? I tell you, this. I had a conversation about linear algebra with Dr. Smith this morning, and I see it has. This is all his fault. No, it's my fault. Just a second here. I'm just trying to make sure I get my ducks in a row here. Page 524 in your book is where he sets the terms. All right. So yes. Sorry. Let me reorder things here just a bit. Change these equalities to pluses. And let's get some derivatives involved here. So this is dx1 dt. This is dx2 dt. And this is finally down here is dxn dt. All right. So you can rewrite this as dx vector dt is equal to a times the x vector plus f vector. So here, where a is the coefficient matrix, here a sub ij could be function of t. Generally speaking, you could have the coefficients are actually functions of t. And f, right, is the, it's a vector of functions of time again, right? In the case that f is equal to 0, so like terminology, if this f is equal to 0, then, let me give this thing a name, then star is a homogeneous system. Otherwise, it's said to be an inhomogeneous system. All right? So we want to learn now, how do you solve something like star? How do you solve a system of differential equations? Now, do you guys have any questions about, like, there's some obvious questions, like, why are we just looking at first order systems? right? We just got done talking about how to solve 6th and 5th order and 4th order problems, everything under the sun, right? So why just limit ourselves to first order systems? One question you might ask. So let me show you that, why that is. So here's the question. Why first order? Why not higher order for our general focus? So getting past this little discussion here, what we're going to do, guys, is we're going to learn how to solve star in the case that A is constant coefficients. If A is got numbers in it, then we can solve it. I mean, when I actually have A having functions in it, not a happy place. I mean, it is considerably harder to solve these when A has functions in it. But that's not surprising, because we have seen already that when we have a differential equation of nth order, constant coefficients are stupidly easy. Variable coefficients, you're suffering through right now, right? It involves the Frobenius method. Is there a Frobenius method? Could you do series solutions to systems of differential equations? Sure, you could do that. Will I do that in this course? No, I will not. I am not paid enough. Maybe if there were 10 students here, I could do it, but no, it wouldn't matter if there were 500 students here. If it was all I did in my life, and I had 10 of those 500 students who cared, I might do it. But it would be a considerable investment of time to really solve a non-trivial system with series methods. It'd just be beastly. But, I mean, in other words, it is something that could be done, but I would say it's something you should do for your job, not for your coursework, okay? And even then, you probably should ask yourself, is there a better way to do what I'm doing? All right, anyway. So why just first order? Let me show you an example. What example are we on? It's a new example. It's a new day. Example 1. So this is example. We're on different. We turned a page. We're doing differential equations now. We're past our linear algebra. I would say review, but for many of you it may be a preview, right? So example 1. How about this? What if you had y prime prime plus like 3y prime plus 4y equal to e to the t, and you had z prime prime, z prime prime prime. Oh, let me not get too carried away here. Let's suppose we just had z prime plus y equal to cosine t. So here's a system of differential equations. So, you know, we have dependent variables of what? Our dependent variables are y and z, all right? I would say, so when I think about a system of differential equations of mixed orders, I define the total order to be like the sum of all the orders. Now, I'm assuming that these differential equations are genuinely independent in some sense. Like if you were to say, well, professor, I want to add a new differential equation, and my new differential equation is going to be this, I'd be like, shut up, get out of here. No, that is not allowed. You shall not do that. So we are making some assumptions about independence of our equations, all right? Don't make me formalize that, please. x1, so we do what's called reduction of order. Not to be confused with our previous notions of reduction of order, but they're all sort of a variation on a theme here. I mean, before we talked about reduction of order briefly, in terms of taking an nth order differential equation and reducing it to an n-1 order, there's a section, I mean, I didn't really test on it, but here's what you do. x1, and this is not by no means unique, but the point is it can be done. So I say x1 equals to y. Then I let x2 equal to y prime.